right, so what we want to do is figure out the relationship between linear velocity, which is v, and angular velocity, which is that weird omega thing. So how do we find this? Well, let's just collect some data. So I don't know if I'll be able to do this super well. Let's see if I can see if my computer skills are up to the task. So you may not be able to see this as well as we'd like, but let's give it a shot. Okay, so I'm gonna reset everything. I'm gonna make sure that I'm back to this is alpha theta, omega, and v. My units are radians. I'm gonna put both my critters on there, and I'm gonna measure my distance right now. So I can't quite see well enough to do this. So but I think it looks like my ladybug is at about 2 meters, and it looks like my beetle is about like 3. That looks like 3 maybe 3.3, and let's just see if we'll see. That might be wrong because I can't see. And then I'm going to give it a little bit of angular velocity here. So I'll give it about 1.56, and it's telling me right here my 2 linear velocities. So let's see if I can do this. So my angular velocity in both cases is 1.6 about, but I have 2 different linear velocities. For the ladybug, it's 3.11, and for the beetle, it's about 5.2. All right, and now I'm going to change my angular velocity. I'm going to make it a little bit more. I'm going to make it about 2. All right, so that's roughly 2. So my angular velocity is about 2.1. And again, I have 2 different linear velocities. My beetle is about 6.9. And my ladybug is about 4.2. Okay? And let's do one more. Let's change the angular velocity to about 3. Okay? So now I have 2 measurements with my angular velocity at 3. My beetle has a linear velocity of about 10. And my ladybug has a linear velocity of about 6. Okay? And then what I seem to see here is that my ladybug was about 2 meters away from the center, and my beetle was about 3.3 meters away from the center. I'm not sure how accurate that is, but let's just, I mean, that's worthwhile to have that information. Okay, so let's look and see if we can tease out some sort of mathematical relationship between these things. So let's start by thinking about this in terms of a graph. Because we know that as the angular velocity changes, the linear velocity changes too. If this goes up, this goes up. So we know that there's an increase. And so if we put angular velocity on the x-axis, linear velocity on the y-axis, maybe we'll see some sort of connection. And we have 2 data sets, one for the ladybug, one for the beetle. So let's use 2 different colors. Let's use red for our ladybug. So our red values, let's say 1, 2, 3, 4, 5. That's our angular velocity. Actually, the highest I got was 3, right? So let's do 0.5, 1, 1.5, 2, 2.5, and 3. And then our linear velocities, the most I got, I think, was 10. You can't quite see it, but that was a 10, right? So let's do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there will be our 10, okay? So at 1.6, the velocity of my ladybug was about 3, so that's about right there. At 2.1, the velocity of my ladybug was about 4.2, so that's about there. And at 3, the velocity of my ladybug was about 6. 1, 2, 3, 4, 5, 6. So that's about right there. Gosh, that sure looks like a line. And if we look at our beetle, 1.6 was 5.2. 1, 2, 3, 4, 5.2-ish. And at about 2.1, it was close to 7. So that's 10, 9, 8, 7, so that's right here. And at 3, that was 10, so 3 is 10, so that's right here. That sure looks like a line too. Is this perfect? No. But if these things are a line, then what we would expect is that, first of all, we know that they're going to go through the origin, because if something has an angular velocity of 0, it's not going to be moving linearly at all. If it's not spinning, it's not trailing a string behind it. And so we know that the origin has to be 0, which means the ratio of these two numbers should always be the slope. Let's see what the slope is of these lines. Let's see what the ratio of v divided by omega is. And I already know what it is. We use a calculator just so we can get the real goodness. So 3.11 divided by 1.6 is about 1.94. 5.2 divided by 1.6 is about 3.25. 4.2 divided by 2.1, I can do that in my head, it's 2. 6.9 divided by 2.1 is about 3.29, and 6 divided by 3, I can do that in my head, and this was 10 and 3, you can see that here, so 10 divided by 3 is 3.3. You see a pattern here? The ratio between the linear and angular speed of each of these creatures is equal to its distance away from the center of rotation. That will depend on the units that you use. If your unit for distance is meters, and your unit for linear velocity is meters per second, as it is with this simulation, and your units for angular displacement are radians, then your units for angular velocity will be radians per second. And if you multiply the angular velocity in radians per second by the distance away from the center of rotation in meters, you will get the linear velocity in meters per second. Those of you who do the whole unit analysis thing might be thinking, wait a second, what happened to the radians? If I take, for example, 3 radians per second and I multiply it by 2 meters, that should give me 6 radian meters per second. And that's a weird kind of unit. But remember I said radians aren't a real unit. Radians are a ratio. It's the ratio between the arc length, the linear equivalent of the distance that something moves, divided by its distance from the center of the circle. The units of length cancel. The real unit of radian is nothing. There is no unit. It's a ratio, which means that this is really 3 per second. It's a frequency. And this is 6 meters per second. It's a linear velocity. So we've just come up with, by collecting some data, at least hypothetically, something that is really kind of fundamental to relating the speed of an object to its angular velocity. And that is that an object's linear velocity should be equal to its angular velocity times the distance to the center of rotation. We got to make sure that our units are right. This needs to be in radians per second, this needs to be in meters, and that will make this in meters per second. But if our units are correct, then this equation holds, right? So we're trying to build this fluency. Ideally, when I start talking about angular velocity, you will start imagining something moving on a circular path. If I tell you that the angular velocity is some number in radians per second, ideally, you'll have an idea of how quickly it's spinning. Even more ideally, you'll recognize that you don't know how far away from the center of rotation it is. So if I tell you something is moving at pi/2 radians per second, what I would like you to begin thinking is, oh, pi/2 radians, that's 90 degrees. One of those per second means 1, 2, 3, 4. This is the rotational speed. But we don't know how far away the object is from the center of rotation. So imagine a disk rotating at that speed. If we were to look toward the center of the disk, those objects would be moving around the circle in the exact same amount of time, but they're not going very far. They're not trailing a very long string behind them. Things all the way out at the end have a lot farther to move to make that 4-second full circle rotation. So ideally, you'll start to kind of get those images in your mind. That's the piece that we really need to get before we can do more work with this. Okay, so this is the first major calculation, and this is kind of fundamental to understanding all of this stuff. All right, keep going, see how you can do.